All right, welcome to this explainer. Today we are diving right in to aggressively dismantle a pretty dangerous industry assumption about large-scale battery storage, specifically battery energy storage systems or BESS. We're going to unmask a silent threat that's just hiding inside these massive containers and really explore the harsh reality of localized thermal degradation. Look, if you're involved in asset management, grid stability, or battery tech in general, you absolutely need to hear this. Let's get into it.
So let's kick things off by looking at the sheer massive scale of modern battery energy storage. We are seeing container capacities aggressively pushing past 5 megawatt-hours per unit. Think about that for a second. That is a staggering amount of energy density packed into a single, oversized enclosure. It's essentially like trying to contain the energy of a lightning strike in a shipping container. And while that sounds absolutely fantastic on paper for grid-scale deployment, it introduces some severe physical limitations that we just can't ignore anymore.
But here's the hard truth straight from the field, and honestly, it's a bit of a wake-up call. That comforting engineering assumption of homogeneous rack temperatures, yeah, it's falling apart completely. When you pack thousands upon thousands of battery cells into these massive enclosures, the idea that they're all going to cool evenly is exactly that, a comforting assumption. It is definitely not a physical reality.
Moving right along to Section 1, the 5+ megawatt-hour battery myth. Let's look at the primary engineering challenges making this whole myth unravel. Here is the absolute baseline reality of modern high-density battery storage. When we're dealing with these massive densities and these oversized enclosures, maintaining uniform airflow and cooling across every single module becomes practically impossible. You simply can't push air evenly over thousands of tightly packed cells. It's exactly like trying to air condition a packed stadium from a single vent right at one end. The people in the front, they're freezing, but the folks in the middle are sweltering. Which brings us to Section 2, hidden micro-hotspots explained. This lack of uniform cooling leads us straight to the invisible threat that's quietly destroying grid assets.
So what happens is we get these distinct thermal gradients forming because of that uneven airflow. A thermal gradient basically just means we've got distinct, measurable temperature variations arising within the exact same enclosure. One side of the rack is nice and cool, while another pocket is literally baking. And guys, this isn't just some minor inefficiency we can brush off, it's a fundamental shift in how the battery system operates, heavily impacting very specific vulnerable areas of your system.
Now, you might be wondering, where are these vulnerable areas exactly? Well, it's specifically the central and rear rack positions that routinely fall victim to these hidden micro-hotspots. Just visualize the physical layout for a moment. The cool air comes in, right? But by the time it navigates this dense maze of modules to reach the deep center or the far rear of the enclosure, it's either lost its velocity entirely or it's already absorbed way too much heat. These core positions essentially become trapped heat zones.
Okay, so why does a micro-hotspot actually matter to us? It all comes down to SEI layer growth. Now, the solid electrolyte interface layer is a completely normal part of a battery's life cycle. But these micro-hotspots are catastrophic because they severely accelerate local SEI layer growth. You're basically building up electrical scar tissue that completely suffocates the cell's capacity. And that leads directly to premature capacity fade. These localized hotspots are quietly, invisibly eating away at the asset's design life significantly faster than the manufacturer ever promised.
All right, Section 3, the BMS sensor blind spot. If this degradation is happening deep inside the racks, why in the world are we only getting late warnings?
And this highlights the core problem perfectly. There's a massive gap between theory and reality. Datasheet thermal averages promise us this perfect, flawless world, but the actual field reality is just completely riddled with micro-hotspots. Relying on those datasheet averages completely masks what is actually happening in the trenches. An average temperature across the board might look perfectly safe, even while the dead center of your rack is physically degrading from all that excess heat.
You know the reason those averages trick us so easily is because standard battery management system, or BMS, boundary sensors totally fail to register system-wide warnings in time. Think about the word boundary here. These sensors are often placed at the absolute outer edges of the system. Localized capacity fade is happening deep within the core long before these boundary sensors ever notice a spike high enough to trigger a system-wide alarm. By the time your BMS finally taps you on the shoulder to say there's a problem, the internal damage to the cell lifespan, yeah, it's already done.
So, the ultimate takeaway from our sources is incredibly stark. For experienced system architects, designing your system solely around these datasheet averages is practically begging for premature, localized degradation.
You simply cannot manage a high-density 5+ megawatt-hour container by just looking at the average temperature. You absolutely have to design for the extremes that are hiding in the center of the rack.
Let's pivot to Section 4, Advanced Thermal Design Strategies. We can't just point out the problem. We have to look at the advanced solutions to engineer our way out of it.
First up, we've got to intensely manage internal airflow dynamics. We can't just blow cold air into a box and hope for the best. We have to strategically route it. Next, we must actively control cooling distribution, ensuring that the air actually reaches those problematic central and rear rack positions. And finally, we need to deploy advanced, proactive strategies for uniform temperature control across these high-density racks. Honestly, this might mean fundamentally rethinking the internal geometry of the containers themselves to prevent those core hotspots from ever having the chance to form.
So I want to leave you with this absolutely critical, provocative question straight from our source material to challenge how you approach your own asset management and engineering designs moving forward. Hardware engineers and system designers, how are you managing internal airflow dynamics and cooling distribution in your high-density 5+ megawatt-hour containers to prevent those invisible core hotspots? It is a huge question, and frankly, it's one the entire industry needs to answer right now. Thank you so much for joining me for this explainer, and keep innovating.